Hi everyone, welcome back to Dave's Math Channel. I'm your host David Tare, and this is my continuing feature on the Math Lovers book. And I apologize for the delay. I didn't have internet for about 4 days. It was a pretty bad fire in my neighborhood that burned down my internet cable, and they had to fix it today. So anyway, now I'm back. Now I have internet access again, so I can make my videos again. And today I'm going to follow up my previous video, which was I talked about the tetrahedral rotation group. Today I'm going to talk about a bigger group, namely the tetrahedral symmetry group. And I think it's best to illustrate with, I made a couple, models of tetrahedron. I hope you can see these. I wrote a lot thicker than last time. So I think first what I'm going to do, let's begin. So I don't know if you guys can read these slides, especially if you're using your smartphone. You probably can't, but at least I think you'll be able to see what I'm doing. So last time I demonstrated the tetrahedral rotation group, and you only need one tetrahedron for that. So notice I've got a tetrahedron I cut out with all the faces and all the vertices marked with letters A through A, B, C, and D. So this is side A, and then side B, and side C, and side D. I'm not sure if I marked the letters the right orientation, but I think you get the idea. And then the vertices are just marked with a letter of the opposite face. So for a tetrahedron, every vertex is opposite to a unique face. So this vertex I'm marking A is opposite the face A that you can see here, and so on. So anyway, I think I demonstrated last time. I'm going to do this very quickly, but I demonstrated that the rotation group of a regular tetrahedron is isomorphic to A4, the alternating group on four symbols. And I think that's pretty easy to see because you just see how it permutes the vertices or the faces equivalently, if you like. So, for instance, if we started with face A, and then we rotated it 120 degrees. Maybe it's easier to start with a vertices. So let's look at the vertex A. Here's the vertex A. And if we rotate 120 degrees clockwise, I think you can see that that's permuting the faces B, C, and D. It leaves A alone. So B goes to C, C goes to D, and D goes to B. And if I do another 120 degrees, then we have now we have D where B used to be, and B where C used to be, and C where D used to be. So those are going to give us two threefold rotations of B, C, and D. And similarly, you can get another 6, so 8 altogether, if you fix one of the other three vertices. So for instance, if you fix the vertex B, then you can rotate A, C, and D. A, I guess here's A, and yeah. So one way, I guess you get ADC if you rotate it 120 degrees clockwise, but then you get ACD if you rotate it 240 degrees clockwise, or equivalently 120 degrees counterclockwise. I think you get the idea, and there's 4 more. So there's a total of 8 threefold rotations, but and remember, you always get the identity element. The identity element you always get for free for any group, because every group has the identity element. That's one of the 4 axioms of group theory. That just corresponds to not doing anything with tetrahedron, leaving it alone. But then remember, there were 3 other rotations. You have 180-degree rotations about an edge. So for instance, here's the edge connecting faces B and C, and you can rotate 180 degrees, and that flips B and C. But it also flips A and D on the other side. You can't see them, but so this corresponds to a product of 2 disjoint transpositions, namely AD and BC. Similarly, you got 2 more. You got one that will flip AC, A and C, and also B and D. And then finally, you got one that'll flip A and B, and also C and D, in fact. So that's an additional 3. That's 12 altogether, and that's all there are. So those are all the even permutations of the set A, B, C, D. So that proves, not only does that prove that the tetrahedral rotation group has order 12, it also proves that it's isomorphic to A4, the alternating group about 4 letters. Well, now I'm going to talk about a bigger group, namely the tetrahedral symmetry group, and I have another tetrahedron for that purpose. you'll notice that this one has letters in red, the other one has letters in blue, and you'll notice something else interesting about these tetrahedra, I hope. Notice that they're mirror images of each other. How do I show that? So this one has, I just dropped one. Get it? So about that. All right. Yeah, so I'll show you. I mean, if I just go back to my original tetrahedron, here's the faces A and B. Oh, it's probably easier to show. Yeah, maybe I should show the face with the vertices. So notice that the red tetrahedron, the one with the red letters, I think you can see that B, C, and D go clockwise. I mean, yeah. Let me just keep a front. So now you can see the vertices. B is on the bottom. If you go clockwise, you get actually get BDC for this one. And let me show it for the other one. So here's the mirror image. Now you'll notice that if you go clockwise for the blue one, you can get CDB, whereas you get CBD for the other one. So I think you can see the one's a mirror image of the other, and there's no way you can rotate one of these tetrahedron to get it to look like the other one. It's not equivalent to its mirror image. So you get an additional 12. It turns out you get an additional 12 um, uh, transformations if you allow reflections as well. For instance, you have the reflection, let's put the A's again. You have the reflection about what is it? I guess you could say the BD axis or the CD axis. CD axis, yeah. So you have the axis going through C and D, and if you reflect that, you can just imagine a plane that goes midway through the vertices C and D. It's also going to be parallel to the edge AB in the back. So that's a plane, and if you reflected about that plane, you would get this blue tetrahedron, where now I think you can see that C and D are reversed, and so are I guess A and B. Is that right? Yeah. So yeah, this is not equivalent to the other one. So that's one symmetry transformation. But by combining reflections and rotations, you can actually get an additional 12. It turns out. I don't know if there's an easy way to demonstrate that. But I mean, I guess maybe the easiest way to see this is imagine you just reflected you start with a red tetrahedron, you reflect it, now you get the blue tetrahedron. Well, now there's 12 rotations you could do to the blue tetrahedron. And each of those rotations will give you a tetrahedron that doesn't look anything like the red tetrahedron, no matter how you rotate it. So that's an additional 12. That will give you an additional 12 different labelings of the vertices and the faces. And it turns out that you get all 24. If you look at how they permute the letters A, B, C, and D, you get all 24 permutations. So that means that the full symmetry group of a tetrahedron is isomorphic to S4. The symmetry group or I think that's called the symmetry group on 4 letters, S4. So I just proved that, and you can forget about the rest of the text I wrote here. But I mean, I guess maybe I should just say one more thing. So you can generate the rotations with a single transposition, like I did before. I mean, I had the transposition A, B, I think, or C, D. It doesn't really matter, but by a single transposition, that gives you rotation, and then you can multiply those by rotations. That gives you more complicated, permutations. But you only need one generator. You only need so remember you can represent a group by its generators. So the generators of A4, I guess, would be a single threefold rotation and a product of two transpositions. Those will generate A4. But then if you also include a single transposition, that's your third generator, that will generate all of S4. So that's how you get S4. Anyway, I think that completes my video for today on the tetrahedral symmetry group. And, we'll have more fun. I'm going to do, in the next few videos, I'm going to talk about the rotation groups and symmetry groups of the other platonic solids. There's another 4 groups. So I've just talked about 2, the tetrahedral rotation group and the tetrahedral symmetry group. But then we also have the octahedral rotation group and symmetry group. That's a symmetry group of a cube or equivalently an octahedron. It turns out they have the same groups, the same rotation groups and symmetry groups, because one's a dual of the other. And similarly for the dodecahedron and the icosahedron, there's a rotation group and a symmetry group, and those are called the icosahedral rotation groups and symmetry groups. So I'm going to go over those in the next few lectures, and I think we'll have some fun with that. I'll make some more, cutouts of platonic solids, and I recommend you guys try this too. You might have some fun playing around with these things. Anyway, that completes my video for today. So thank you for watching. Long live math, and I'll see you guys next time. Bye.